Hello everybody, and welcome to the Poor Man's Chemist. In this video, I want to review a very interesting document that I found that details 12 different reagent tests that are used to presumptively identify drugs of abuse, quote unquote. Now, this is something that is used by law enforcement. This document, from what I can find, was written in 2000. But, whether it was written in 2000 or now, it's going to work exactly the same, and I promise you the reagent tests have not changed that much. I will be pulling in information from other articles that I've found in various scientific journals to supplement what this document says, because it's kind of bare bones, but very helpfully it does give you the instructions to prepare all of these reagents. I was able to find what positive results look like, what negative results look like. In some cases, I was able to find stuff that can give false negatives or false positives. All handy information to know. The first thing that I want to discuss is found towards the end of the paper on page 8, where the document details the test conditions and procedures. The important thing to take away from this is that these reagent tests will only be reliable if the temperature is between 10 and 40 degrees Celsius. That's 50 to 104 degrees Fahrenheit for us Americans, and the relative humidity should be between 10 and 90%. In other words, whether you're in a desert or a rainforest, these things should pretty much work. If the temperature is too low, the test will be slow to react, or it won't react at all. That will obviously make the test unreliable, unless you've tested the reagent at those low temps with some kind of reference standard sample to see how it behaves. Similarly, if it's too hot, the reagent will react too quickly, and other chemical reactions that would not have been noticeable at lower temps may no longer be negligible at the higher temp. To carry out these tests, place 500 micrograms of the analyte, that's half a milligram, either as a powder or dissolved in chloroform, presuming most people will use a powder, in each of 3 wells on the porcelain test plate. Obviously, a user is going to test their shit once with a reagent test. If they're especially bright, they might use 2 or 3 different tests to be absolutely sure of the result. Or as sure as you can be using only reagent spot tests. But remember, this document was written for law enforcement peoples, and presumably all of this stuff is meant to hold up under some lawyer tearing it apart in court. Anyways, using a disposable Pasteur-type pipette, transfer 1 drop, that's approximately 1/10 of a milliliter, of each reagent being tested in the sequence specified by the manufacturer if appropriate to each of the 3 wells. When they talk about the sequence specified by the manufacturer, they're referring to reagent tests that require more than 1 solution to carry out. So, for example, if a reagent test requires 2 solutions, the instructions may be something like add 1 drop of solution A followed by 2 drops of solution B, that style of thing. Once everything has been added, the usual procedure is to wait 1 to 2 minutes, noting any colors that may appear. Sometimes a reagent test may only give a single color with a particular compound, while with other compounds, the sample turns 1 color initially, but then changes to another one over the course of the 1 to 2 minute test period. If more than 1 color is involved, then the rate at which 1 color changes to another will be temperature dependent. Remember, the rate of a chemical reaction roughly doubles for every 10 degrees C increase in temperature. So a test done at higher temps may change colors more quickly than it will at lower temps. That's why doing these things in the correct temperature range is important, kids. Another thing that's important is to make sure you check your stuff at the correct time interval. Some tables will use different time intervals. In fact, there's one that I found in a paper that uses the initial color and then the color after 5 minutes, not 1 to 2. So make sure you check your stuff at the right times. Another important thing to note is that these reagent tests do require a minimum concentration of the drug to be present in order for the test to work. Some of these tests are very sensitive, while others are less so. If the drug is present in concentration below these limits, the test will not give a positive result. It's also possible for cutting agents to interfere with the test, which is a theme that will come up again and again in this video. This can work for you or it can work against you. Although no cutting agent is going to hide it from LCMS or GCMS analysis at the crime lab. Once it gets sent to the crime lab, you're proper fucked. Now let's take a look at the results table. This is just the first page of them. This fucker is 4 pages long. Probably it's 12 reagents. We can see the reagent, the analyte, the solvent that the sample is dissolved in if it isn't a powder being directly tested, the ISCC description of the color of the result, and the exact shade of the color in both the ISCC and the Munsell color systems. Remember, the results of these reagent tests would have to hold up in court, so the authors of this document went to great lengths to standardize everything and make the test as robust as possible. So far as the color systems go, the ISCC one is pretty simple. Each color corresponds to certain values in the RGB color system, and each color is given a specific description along with a corresponding number. These are the descriptions that you can see on the tables in the document that we are reviewing. You'll notice that their names match up with the ones on the ISCC table. The Munsell color system is a bit more complicated, although Wikipedia has a good article on it if you're interested. All you really need to know is that you can type the word Munsell followed by the color coordinates in Google, and you'll be able to see what it looks like. That's pretty handy, right? So the 12 tests that this document describes are on your screen here. We have cobalt thiocyanate test, which is the basis of the Scott and Morris tests. Then we have 2 names that I can't pronounce, so we will just call this DK reagent. Once again, we'll call this one DL, because I don't know how to say that guy's name either. It looks French. And then we have mandolin, marquis. I know how to say that one. Then we have nitric acid, just concentrated nitric acid all by itself, which I actually didn't know about. Then para-dimethylamino benzaldehyde, test for indoles. That's what we use to test for tryptamine. So it's for Ehrlich's reagent, I guess, and Hoffman's reagent. We have ferric chloride all by itself, which seems to have very limited utility, although it can be used to test for morphine, which I guess is something. And then another guy whose name I can't pronounce. It seems like I've heard somewhere that this is pronounced Fruta. I have no idea. Help me out, people. Was I close? Then we have Mech's reagent, and then a guy whose name looks German, in which case it would be something like Zwicker. And then a nice, I don't even know what, just common name, Simon. I know how to say Simon. Well, the rest of these are just, I don't even know. I'm not even going to try. Now, cobalt thiocyanate is the basis of the Scott test and the Morris test. The Scott test uses cobalt thiocyanate in a dilute acidic solution, whereas the Morris test uses dilute alkali. Some versions of the Scott test, like the one presented in this document, just use distilled water, and so the pH would be determined by the salt dissolved in it. For free-base compounds, the mildly acidic version would be best since it will dissolve them, making the test more accurate. For salts, the neutral version could be used with no problems. The document tells us to prepare the reagent by dissolving 2 grams of cobalt thiocyanate in 100 mils of distilled water. The Scott test is often used to test samples that are suspected to be cocaine, although diphenhydramine and lidocaine give false positives, and as you can see on your screen, other agents can interfere with the test, causing a false negative or a false positive. While the Scott test is mostly used for cocaine, it can be used for many different drugs, as you can see here. It also gives a green color with embalm, and it does so very consistently. The only one that doesn't turn green is 25N embalm. Cetirizine, loperamide, levamisole, and bupropion give similar colors. The Morris test seems to mostly be used to identify ketamine, which gives a purple color. Cocaine, morphine, ephedrine, and several amphetamine derivatives also give a positive test, although the color is blue. The procedure is to basify the sample with 0.004 milligrams per milliliter sodium hydroxide, followed by the addition of a solution of 0.02 milligrams per milliliter cobalt thiocyanate. So to the person who asked me on the community posts in YouTube, there you go. That's how you test for ketamine. And that brings us to the second one, which, as I said before, since I cannot pronounce these names, we are going to call this DK reagent. It's used to test for barbiturates. The reagent consists of two solutions. The first is made by dissolving 100 milligrams of cobalt to acetate dihydrate in 100 milliliters of methanol. Then you're supposed to add 0.2 milliliters of glacial acetic acid and mix it up. So in other words, very mildly acidic, very mildly. The second is made by adding 5 mils of isopropylamine to 95 mils of methanol. And interestingly, you can buy isopropylamine and it's not all that expensive. I was surprised by that. The procedure to use it is to add 2 volumes of solution A, which is our cobalt, acetate dihydrate, and methanol with a touch of acetic acid, and followed by 1 volume of solution B, which was our isopropylamine and methanol. It was difficult to find an image of what a positive test really looks like in real life, and this low-quality picture was the best I could find. Nevertheless, you can see the color that indicates a positive test for barbs. And since we're on the subject of barbs, let's jump to A11, which I suspect is pronounced as the Zwicker reagent. Or I'm sure other Americans just say Zwicker and go with that. This is another binary reagent. Solution A is dissolve half a gram of copper 2 sulfate pentahydrate in 100 mils of distilled water. Easy. Solution B is 5 mils of pyridine and 95 mils of chloroform. The procedure is to add 1 volume of solution A followed by 1 volume of solution B. The color of a positive result is pretty much the same as it is for DK reagent from what I could find. The Munsell coordinates are very similar, as you can see. Although, do those really look like the real life test result? I guess, kind of. Yeah, okay, who am I kidding? No, they really don't. But nevertheless, that is what this document gives us. A3, the DL reagent is an interesting one. This reagent is used to test suspected cannabis for THC. And by cannabis, I mean the actual plant material, not some synthetic product. Although this test may work on them, but I mean, usually THC comes as gummies or vapes, which have a lot of additives that could interfere with the test. Because this test is done with actual plant material, it is always carried out in test tubes. I'm going to break with the normal flow here because I found an excellent paper that describes the prep and use of this reagent better than the document we are currently reviewing. They say the following. To prepare the reagent, 2 grams of vanillin was mixed with 2.5 milliliters of acetaldehyde, and the mixture added to 95% ethanol to make 100 mils of the reagent solution. To use the reagent, 1/4 gram of dried, pulverized, and homogenized cannabis sativa leaves were mixed with 1 ml of the reagent, shaken, followed by the addition of concentrated hydrochloric acid and vortexed for 2 minutes. What they mean by vortexed is Well, there's this little device in the lab. You can like put a test tube on it and it kind of spins around really rapidly in a small circle and it makes everything in the tube mix up. You could just mix, swirl the test tube and you'll achieve, well, a similar effect. Followed by the addition of 1 ml of chloroform. The mixture was then left to settle for 5 minutes. A positive test is indicated by a dark purplish layer in the chloroform and a light purplish blue, although to me it just looks kind of purple, layer in the aqueous phase. They call it aqueous, but it's like mostly ethanol. The document we are reviewing also gives us results for mace, nutmeg, and tea. How that looks like cannabis is beyond me, but whatever. What kind of dipshit buys fucking tea thinking it's weed? Next we come to Mandelin's reagent. To make this, dissolve 1 gram of ammonium vanadate in 100 milliliters of concentrated sulfuric acid. Mandelin's reagent is a general test that is used for all manners of things, as you can see here. There are even more extensive tables for this very common reagent all over the internet. I found a real large one in a paper that is linked in the description, so you can download it from Sci-Hub. Just click the link. It takes you directly to the paper on Sci-Hub. And you can have a copy of this too. I could not think of any way to fit it on to try to fit it on the screen and make it legible is impossible. So you'll just have to download it and look at it. The next one is another common general reagent, Marquis reagent, which is made by slowly adding 100 milliliters of concentrated sulfuric acid to 5 milliliters of 40% formaldehyde, although like the 33% stuff will also work. It is also used to test for a wide variety of substances. One nice thing about these general tests is that they're usually pretty easy and cheap to make, so you can do more than one on a sample. Like I've said before, if 2 or 3 reagents give the right result for a compound, then you can be a lot more certain that you do indeed have what you think you have. I know, not always practical, but nevertheless, it is true. And that brings us to the concentrated nitric acid. Again, nothing else, just concentrated nitric acid. Apparently, it can be pretty useful going by this results table. Who knew? Para-dimethylamino-benzaldehyde, as mentioned before, used to prepare Ehrlich's and Hoffman's reagents. The formulation given in the document for just the general reagent, I don't know if they actually use either name in association with it, is 2 grams of DMAB to 50 mils of 95% ethanol and 50 mils of concentrated hydrochloric acid. Other variations of this formulation exist, but all use para-dimethylamino-benzaldehyde. You can buy this compound in bulk and it's fairly inexpensive. This reagent can be used to test for indoles, among other things. In other words, tryptamines, although other indoles may very well give a positive result. Since the indole moiety occurs in myriad compounds that aren't controlled substances, a false positive wouldn't be difficult for a shady dealer to pull off. Just something to keep in mind. Funnily enough, this reagent does have another application, which is to test for hydrazine. Since making hydrazine seems to be something that most amateur chemists want to do for reasons I've never been able to fathom, this reagent may be useful in confirming the identity of the product. Seriously, why does everybody want to make that shit? Another extremely simple reagent test is made by dissolving 2 grams of anhydrous ferric chloride or 3.3 grams of ferric chloride hexahydrate in 100 mils of water. That's it. Apparently, it has some usefulness in detecting morphine and chlorpromazine, aka thorazine. This is good because thorazine is an absolutely horrible drug. God. This reagent test isn't used for many drugs. In fact, it finds its greatest utility in detecting phenols. According to Wikipedia, it's also used in a clinical sense to test for phenylketonuria and for salicylates in the urine. I was able to find some supplemental material that it confirmed the salicylate one, but I don't know. There were no sources given on the Wikipedia article. And phenylketonuria gives me flashbacks to biochem class, and so I didn't want to look at it. This brings us to yet another general test, which is probably called Froda's reagent or something like that. I could not find out who this guy actually was anywhere. There's a shit ton of results for his reagent, but no mention of the guy who invented it. So I have no idea what his nationality was. Somebody help me out in the comments. Anyways, the reagent is made by dissolving half a gram of molybdic acid or sodium molybdate in 100 mils of hot concentrated sulfuric acid. I know this sulfuric acid thing is a recurring theme too, right? This reagent is very useful, and we should remember the poor bastard that invented it. You can find more extensive result tables on Wikipedia and elsewhere on the internet. I don't know why this reagent doesn't get more use given the laundry list of compounds that it will give a colored product with. It always seems to get overlooked. I don't know why. Another one that gets overlooked is Mech's reagent. And yet again, we have another general reagent that gives colorful products with a fuck ton of different compounds. This reagent is made by dissolving 1 gram of selenous acid in 100 mils of concentrated sulfuric acid. Selenium dioxide may also be used, although selenous acid is just selenium dioxide dissolved in water. This is not hard to achieve, as the dioxide is actually fairly soluble in water. And since I already showed you guys how to make pure selenium dioxide from relatively cheap elemental selenium without having to resort to combustion, there's really no excuse for not using this excellent reagent test. For those who are tempted to make selenium dioxide by burning elemental selenium, be warned, burning selenium absolutely reeks of horseradish. At least that's what it reminds me of. And catching the white fumes is rather difficult. Also, I don't know that you want to be that close to a large amount of burning selenium to where you would have to like fuck with an apparatus. It has a pretty powerful smell. And so my synthesis avoids all those difficulties and produces a pure crystalline product in high yields. You're fucking welcome. And now, lastly, we have Simon's reagent, which is another binary reagent test. Solution A. Dissolve 1 gram of sodium nitroprusside in 50 mils of distilled water and add 2 mils of acid aldehyde to the solution with thorough mixing. Solution B. 2% sodium carbonate in distilled water. That's a hard one. Procedure. Add 1 volume of solution A to the drug, followed by 2 volumes of solution B. This test appears to be most useful for the detection of secondary amine drugs like methamphetamine and MDMA, although there are some primary amine drugs like 4-fluoroamphetamine that will also give a color change, although not the same color of methamphetamine or MDMA. But it gives a color change nonetheless. If the acid aldehyde is replaced with acetone, the reagent can be used to better detect primary amines like amphetamine. In this case, the color of the product is supposed to be purple. Presumably, some mundane primary and secondary amines would give false positives. I don't know. There appear to be a shitload of primary and secondary amines that don't react with it, so just be forewarned, it's not going to react with everything. Obviously, there are many other reagent tests out there that you can make use of. Zimmerman's reagent can be used to identify benzodiazepines, and Lieberman's reagent is another common general reagent that is easily prepared from common chemicals. There are many more. Late in making this video, I came across a fascinating little document called Chemistry and Reaction Mechanisms of Rapid Test for Drugs of Abuse and Precursor Chemicals. It's linked in the description. It's the last document linked, so it's at the bottom. It goes in depth into the mechanisms behind the reagent test reactions, and it also gives reagent tests for each specific drug of interest, also some notable precursors. It's absolutely worth taking a look at this fascinating document. I kind of wish I'd found it earlier so I could have incorporated it into this video, but this video already took several days longer than I anticipated it would take, and there was no way in hell I was doing this over again. And so I leave it up to you to pursue the secret wisdom of this document on your own time. And to the person who asked me about fentanyl, reagent tests, such thing exists, but all the ones that I found were commercial products that, because of how the tests work, it's just not possible to produce this kind of thing at home. The commercial products appear to be quite sensitive, but not terribly reliable for telling you much beyond that fentanyl is present in the sample. I could not find any results for the common reagent test we've talked about for fentanyl, but this may be because fentanyl is so potent that it'll be cut with so much other crap that its effective concentration is too low to be reliably detected using these simple reagent tests. So you're stuck with the commercial products, I'm afraid. I will close this by saying that these reagent tests have a better, more advanced use than what this video has described thus far. If you really want to be sure that some sample was a pure substance, you could always do thin layer chromatography on it. Once the plate is dry, examine it under UV to identify all the spots on the plate. Then spray it with the reagent in order to visualize the spot corresponding to the compound of interest. This will cause the spot to become colored and easily visible. Admittedly, this technique is best used by a practiced chemist, but once mastered, it can take reagent testing to a whole other level. It can even make it possible in some cases to identify common cutting agents. For example, this technique could easily distinguish real heroin from fentanyl. It could also identify if the drug was cut with something like xylazine. This is a particular concern because xylazine is becoming extremely prevalent in street opioids, and while safe for use in animals, xylazine is especially dangerous for our particular species, since the therapeutic threshold and the threshold of toxicity are close together in humans, and these thresholds can vary widely between people. To give you an idea, overdose can apparently be caused by anything from 40 to 2,400 milligrams of the compound, and you don't know what your number is going to be, I guess, until you try it. I don't know. As a bonus, xylazine overdose is often fatal in humans. Hooray! Xylazine has been widely used as a cutting agent because it potentiates opioids and has sedative effects of its own. It's also addictive and dependence forming all on its own, though it is not a mu receptor agonist. So, addiction to xylazine has a different mechanism from opioid addiction, meaning they can give you whatever they want to for the fucking opioid withdrawal, but it may not do much for the xylazine withdrawal. That sounds like hell. However, thin layer chromatography would quickly reveal xylazine's presence if it was there. I've not seen any reagent test results for xylazine specifically, although if anyone knows, let me know and I'll pass them along. Also, to my other fellow chemist peeps out there, if you've got an RF value for this shit in a mobile phase system, give me the composition of the mobile phase and the RF value for this shit. I will make sure other people hear it, because you can help people out with this, man. I don't know, we might save one or two junkies out there. Probably not, but hey, you never know. I used to be a raging opioid addict, so, I've been off that shit for 9 years now. I know people are not past saving if they want to save themselves. They gotta want it though. You can't force anyone to do it. Oh well. Oh, that's it, people. If you like this video, give it a comment, subscribe, and if you want to support the channel, there are links in the description. It would be appreciated. Anything you would like to clarify, add on, any good comments, I will make sure, I don't know. I might do a follow-up video just to make sure that whatever tidbits of wisdom you guys give me get passed on to other people. Because the more information like this that we can get out there, the better chance we've got of some, kid that's fixing to do something dumb that hopefully thinks twice and checks their shit. And I don't know. You never know. It might save one dumb kid out there. And if it saves even one, then it's worth it. So anyway, till the next one, guys. I'll see you later.